Hello and welcome back to the second day of the tandemPV workshop. My name is Lars Kotter. I'm with the Helmholtz Center Berlin. And yeah, this is the second session on high efficiency perovskite solar top cells for tandems. The first one has been yesterday. This is a rather short session. We have two speakers, Hairen Tan and Steve Albrecht, before we then go afterwards to the poster session. Before I actually introduce Hairen as the first speaker, I want to share my screen quickly to show you something about how to handle the video stream, because there were questions yesterday. So you should now be able to see my video or my dashboard actually at the website. And quite a few people told me, well, the video stream was cutting out during the session, at the end of the session actually. This is what happens when you use this window and maximize this in order to watch the video stream. So the way to go is, if you want to have the video all till the end of the session, even if it's a bit longer than intended, you rather click here on the timeline, and then you get the video once again here. You can start it. And then you have here the video, and you can also send your questions here on the side. And also here's the smiley, so you can upload questions that others have had, so that I, as a moderator, know which of the questions are interesting and relevant to you. That would be a great help. Okay, so with that technical introduction, I'd like now to introduce Hairen Tan to you. Hairen did his PhD in electronic engineering at the Technical University of Delft with Miro Zeman. And afterwards, he went to the University of Toronto to work with Ted Sargent on perovskite cells. And he is professor at the University of Nanjing now since 2018. And he to present today on strategies toward efficient and stable monolithic all-perovskite tandem solar cells. So Hairen, please, the floor is yours. Looking forward to your talk.
Thank you, Lars, for your nice introduction, and thank you for inviting me to give a talk today on this great conference. So now I will share my screen. Oh, can you see it properly now?
Yeah, great, thanks.
Okay, then I will start now. So today I will talk about some work in my group that we work on all-perovskite tandem solar cell. That means that we build up tandem devices using only perovskite materials as absorber layers. So a few months ago, so Steve has published a very nice perspective, and his group predicted that for the perovskite-based tandem, so we have typically three device configurations that we use: high band gap perovskite together with narrow band gap materials like crystalline silicon, CIGS, or even the narrow band gap perovskite. So for all those three tandem device structures, Steve has predicted that all those three can achieve a practical limits about 30% efficiency, as we can also see here. So I will open my later point. So as we can see here, for the practical efficiencies, it can be very comparable to the perovskite silicon tandems that several speakers has presented this topic yesterday. And today I will focus on the perovskite and the perovskite tandems. And for the SQ limit, as we can see here, the perovskite tandem has the highest limit efficiency. So in the past 5 years, due to the fast progress in the single junction narrow band gap perovskite solar cells, so also the efficiency of the all-perovskite tandems has progressed very fast. So a few months ago, our group has published the all-perovskite tandem efficiency with in-lab efficiency of 25.6%, and that is very close to the highest reported single junction perovskite solar cells. But still, because the theoretical efficiency for the tandem devices is well above 40%. So we still have much rooms to improve the efficiency. And today I will show like some works we have done in the past 3 years, like to show our strategies, how to improve the efficiency and also the stability of the perovskite tandem devices. So the very important component of this perovskite and perovskite tandem devices is the low band gap perovskite subcell. And many speakers have talked about the wide band gap perovskite yesterday, and this field has also achieved very rapid progress in the past few years. And for narrow band gap perovskite solar cells, usually we have to mix the certain amount of tin in the lead-based perovskite, and usually when the tin content ratio is around 50 to 60%, then we can achieve exponentially the lowest band gap, and we can get currently is around 1.2 electron volt. But still, when we first want to make the mixed lead tin based narrow band gap perovskite solar cells, we encountered two challenges. So the first challenge is that the ready oxidation of the tin 2+ ions to 4+ ions, not only in the precursor solutions but also in the perovskite material itself. So this usually will result in very high trap density and short diffusion length in the material. And also due to the inclusion of the tin in the B-side cations, we often see the crystallization is very fast, and also the film is inhomogeneous. And this will often lead to poor morphology and non-uniform qualities in the resulted perovskite film. So as we can see, listen to the review article by Professor Yan and Fa group, so we can see that the performance of the all-perovskite tandem devices is still largely limited by the mixed lead tin narrow band gap subcells. So the VOC loss is quite large, and also the highest short circuit current available actually for this material is still quite limited. So in the beginning, when I started my group, so we found that actually the tin 2+ ions, the oxidation of the ions directly in the solution is a big problem to make high efficiency devices. For example, if we have the oxidized ions already in the precursor solutions, then unavoidably, so we will get a very high tin vacancy in the material, and this usually result in the very poor materials. So later we find that we can actually solve this problem using the strategies. So we call it is comproportionation reaction. So actually we can add a small amount of the metallic tin powders in the precursor solution. And this metallic tin powders has a very strong reduction ability, and it can reduce the 4+ tin ions back to the 2+ ions. That is what we want. So from these strategies, so we suppose that maybe this will result in lower trap density in the final achieved perovskite film. So we also measured from the XPS spectra, we clearly see that for the perovskite film, if we made from the tin reduced precursor solution, so we can see that in the perovskite film, so the oxidized tin content will be considerably reduced. Yeah. And this will give us a very good benefits in the perovskite film. So we first use the transient, the time resolved terahertz spectroscopy to characterize the charge dynamics of the perovskite film. And we found that actually the mobility of the perovskite film only slightly improved using this strategy. However, so there's a big difference in the lifetime of the carriers. So for the control film, like without tin reduced precursor solutions. So the lifetime is very short. It's only a few nanoseconds. That is what we typically observed for the tin-containing perovskite films. And using these strategies, so we can much improve the lifetime, like almost by like 10 times. So this will give us a much longer diffusion length in the perovskite film. So the diffusion length can be improved from below 1 micrometer for the control sample to almost 3 micrometers in the target sample. So, and this diffusion length of the nanobandgap perovskite materials is almost comparable to the very high quality full lead-based perovskite tin film that give us efficiency about 23% in the light. So due to the increase of the diffusion length, so in this way we can simply think that we can further increase the thickness of the absorber layer. So
Danke für deinen Anruf. In dem Moment war ich gerade im Teamgespräch, um über Samstag zu sprechen, weil ich nämlich dieses Mal ganz raus war aus der Planung und quasi nur den Kontakt zu dir gehalten habe und dich eingebracht habe. Und das Team hat mir gesagt, dass der Tag jetzt am Samstag schon recht voll ist. Und ja, somit hast du in dem Moment keinen aktiven Part. Das tut mir ein bisschen leid, weil du dir den Zeitraum extra geblockt hast. Auf der anderen Seite besteht jetzt gerade die Idee, ob man hier zum Beispiel so einen kurzen Talk einleitet und den nächsten für eine Zukunft-Tag, den dritten, mit dir gestaltet. Dann bist du quasi so im Rampenlicht und wir könnten überlegen, ob du einfach eine Session von einer Stunde lang machst Oder ob du beispielsweise sagst, hey, ich würde super gerne ein Webinar anbieten über euer Netzwerk und das bewerben. Dann könnt ihr auch das machen und zum Beispiel Michael ist mit dabei und Biene, die ein bisschen vielleicht Ikigai mit einbringt oder Meditation. Und demnach, also es besteht auf jeden Fall immer noch sehr großes Interesse, zusammenzuarbeiten, auch in Hinsicht Berufung. Und was wir jetzt machen könnten, wäre zumindest schon mal ein Datum festzulegen, so roundabout im Juni, am besten wahrscheinlich noch vor den Sommerferien. Und ich kann gucken, wie es dann bei den ganzen Feiertagen passt. Und dann über den Inhalt sprechen, auch wie du dich wohlfühlst, ob in einer Stunde oder ob du gerne länger machen möchtest, ob du die Birkmann-Methode vorstellen willst oder eher was zu Berufung finden sagen möchtest oder du ein anderes Anliegen hast. Und dann würden wir quasi alles andere da drin herumschmücken. Ja, und es klappt halt leider jetzt für Samstag.
Can you see now?
Oh, yeah, you see the slides.
Okay, then sorry for this, really sorry for this. Okay, so then I have to go much faster than planned. So,
Just
yeah.
a second. No, you will have ample time. You just need to fix the issue with the sound here also, I think, Daniel.
Yeah, is the sound okay?
Daniel, can you hear us?
Okay, yeah, thank you. So since we can use a multi-thick absorber layer, so as we can see here, we can clearly see a big increase in the short circuit current density, and correspondingly, we can increase the efficiency of the narrow bandgap perovskite solar cells. So after the device optimization, so at that time, so we can get the highest efficiency for narrow bandgap perovskite solar cells. For the first time, get close to 21%, and also from the EQE spectrum that we can see that we can get a very high short circuit current density that is almost approaching 32 milliamp per square centimeter. So the next step is that we have to use this improved narrow bandgap perovskite to build a tandem all-perovskite tandem devices. So when we want to make the all-perovskite tandem devices, so one critical issue we have to solve is that how to make sure the wide bandgap subcell will not be damaged when you do the second perovskite layer by solution processing. So at that time, we thought about an idea. So maybe we can use a very thin, compact tin oxide layer that can be processed by atomic layer deposition to replace the traditionally used ITO film, because we don't like ITO film in the middle of the two subcells, because and that will largely increase the shunting probabilities for these tandem devices. And this ITO layer is very conductive, and it will be also not good for the monolithic integration when you want to make the modules. And also the ITO layer is not very optically transparent, especially in the infrared, near infrared spectral region. So by replacing this ITO layer with the compact tin oxide layer, so we can also make the second perovskite layer on top of it, the wide bandgap subcell, without any damage. But still, we have another issue, because the atomic layer deposited, the tin oxide layer, the conductivity is very poor, so it's not good enough to have to act as the tunnel recombinant junction. So to accelerate the charge recombination in the tunnel junction, so we also add a very thin layer of gold nanocluster layer that we do like 1 nanometer gold layer by thermal evaporation on top of the tin oxide layer. And with these gold nanoclusters in the tunnel junction, so we can much improve the field factor of the tandem devices. And through this way, we further optimize the thickness of the two subcells so that we can get a quite good current matching for the two subcells. So after the optimization, so at that time, so we can increase the thickness of the all-perovskite tandem devices up to 24.8% from the JV measurement. So we also make a larger area like tandem devices to see the uniformity of the two subcells. So we surprisingly found that even when we increase the area up to 1 centimeter square, so we can still see quite high VOC and field factor values. But the short circuit current density reduced quite a lot, and but still it gave us efficiency above 22%, and that is not too bad at that time. So later we thought a lot how to really increase the current density of the larger area tandem devices and also the performance of the larger area tandem devices, because in the field of the perovskite photovoltaics, so one big challenge is that we typically observe a quite fast drop of the efficiency when we increase the area up beyond 1 centimeter square. So as we can also see in our tandem devices, although we found that it's quite interesting phenomenon that for all perovskite tandem devices, the PCE drop or the efficiency drop is usually less than the single junction devices. But still we can see the efficiency drops by 2.5% absolutely when we only increase the area from 0.1 centimeter square in this range to 1 centimeter square. So this is mainly due to the non-uniformity of the narrow bandgap perovskite because of its fast crystallization and also the high trap density on the film surface, and also we think in the grain boundaries. So one strategy we think is that maybe we can find a passivation agent that can also modulate the crystallization process itself. So at that time, we found a molecule we called is formamidine sulfonic acid. Is a kind of sweet ionic antioxidant molecule. So we think there are 3 main functions of this molecule that it can act when we make the films. The first is that the introduction of this molecule, it has a very strong coordination ability with the tin and the lead ions. So we think it might be able to enable a delayed and a more uniform crystallization process when we do the film. And also because it is a sweet ionic molecule, it may passivate the both positive and negative charged defects on the grain surfaces. And also this molecule has a very strong reductivity, so it may suppress the oxidation of the tin 2+ ions on the perovskite grain surface. And also it can also suppress the oxidation of the tin ions in the precursor solution. We later found that. So, and from the PL mapping of the perovskite film over the whole substrate, so we found that with this additive, so we can much improve the film uniformity over the whole substrate. And also we found that the PL emission is stronger with this additive. That is mainly due to the passivation ability of this molecule, and we can also confirm this from the PL decay spectra, that because with this additive we get a longer PL lifetime for the perovskite film. So as a result, we can increase the 1 centimeter square device for the efficiency from 16.1% to almost 19% for the single junction devices. And also we make a smaller area single junction narrow bandgap perovskite solar cells, and we also see that with these additives, we can much improve the open circuit voltage of the devices and also the efficiency of the devices. So the best efficiency we can get in the lab for the small area devices is 21.7%. And we also send one devices to Newport for certification, and it gave us an efficiency of 20.7%, and also with quite a reasonably high open circuit voltage value and a high field factor value. So this is the first certified value that is higher than 20% for the tin containing perovskite solar cells. And we also found that this molecule has the ability to suppress the oxidation of the film. And for the unencapsulated single junction devices, when we stored these devices directly in the ambient air, and we found that with this molecule, it can stay in the ambient air for almost 1 day, without any performance degradation. But still, because it is not really compactly covered the film surface, so we still for longer time after 1 day, the efficiency also started to degrade quite quickly. So the next step is that we want to make a larger area like tandem devices. So for the first issue we encountered is that when we typically use the whole transport layers such as the PTAA, we found the weighting is a big issue to make large area tandem devices. So later we adopted the nickel oxide and nanocrystal film as the whole transport layer, because this nickel oxide film has a very good weighting ability, and also to reduce the interfacial recombination losses. So we also add a thin layer of VMPB for the defects passivation. And with this design, so we can much also improve the efficiency of the top wide bandgap subcell. And using those strategies, so we can further increase the efficiency of the larger area tandem devices. So from the control device is less than 23%, and for the best tandem devices measured in lab, the efficiency is almost 25%. And at the moment, so we can even go beyond the 25% for 1 centimeter square devices. And from EQE, we can also see that the current matching condition is quite good between the two subcells. And we also send one devices to JET in Japan for independent measurement, and it gave us a stabilized certified efficiency of 24.2% with a device area of 1 centimeter square. And the results has been included in the solar cell efficiency table recently, last year, I think. And we also even tried to make a larger area like tandem devices to go beyond around 12 centimeters square for the aperture area. And it can still maintain a good efficiency higher than 21%. And also we tried a smaller area tandem devices, and due to the passivation ability of this molecule, so it can give us a higher efficiency than we can get previously. So the best efficiency we measured in lab is 25.6, but this is not certified value. So we also tested the stability of this all-perovskite tandem devices, and we found actually this ETL, the electron transport layer of the narrow bandgap subcell, is quite critical for the stability. For example, if we replace the organic molecule-based ETL, BCT, with the atomic layer depth tin oxide, so it can maintain a good efficiency even without encapsulation in the air. So after 500 hours, like storage in the air, so the device performance can still maintain their initial performance. And we also tried, we also measured the MPP stability of these devices by encapsulation with epoxy and a glass slice. And we found that with this molecular passivation and also with this atomic layer deposited tin oxide as the ETL, so we can much improve the operational stability of these devices. So the device can maintain almost 90% of their initial efficiency after 500 hours operation. So recently, we further studied the thermal stability of the all-perovskite tandem devices. We found that the organic-based charge transport layers is a big problem for thermal stability, especially for the P dot layer in the nylon bandgap subcell. So if we replace this all organic charge transport layers with inorganic metal oxide-based charge transport layers, we can considerably increase the thermal stability of the devices. For example, so we keep the devices in the glass box and also with a simple encapsulation, so the devices can still maintain 90% of their initial efficiency after 2,500 hours thermal stressing. And we also tested the operational stability in ambient air at a 65 degree, keep the devices at a 65 degree. So the device can maintain almost 80% of their initial performance after 900 hours operation. And this work is under preparation for submission. So the next will be stimulate us to think about how to really go beyond the 30% efficiency for all-perovskite tandem devices. I think Steve later will also discuss in more detail how to achieve above 30% efficiency in perovskite-based tandem devices. So here I will just show my personal some views how to get this goal to go to about 30% efficiency. So if we look at our current results, so we see that we still have quite a low VOC value. That is mainly due to we have quite large VOC losses in the wide bandgap perovskite solar cells. Yeah, and if we can further reduce this VOC loss and also further suppress the halide segregation in the material, so we have a good chance to get the VOC value above 2.2 volt. I think that is not a big challenge. And also for the tunnel recombination junction, so if we can further replace the P dot layer, so we will be able to reduce the parasitic absorption losses. And this will give us a chance to increase the short circuit current density. And also, if we can further improve the quality of the narrow bandgap perovskite itself, we will also have a chance to increase the short circuit current density further and also the fear factor. So I think to go to beyond 30% is quite reasonable. It might be achievable in the next 2 or 3 years. And finally, I will just like really simply to show our recent results on triple junction solar cells that is all made by perovskite materials. So theoretically, because from two junction tandem devices to triple junction devices, theoretically we can further increase the SQ limit efficiency of the solar cells. And also it may has other applications because of its higher voltage output. For example, it may be used for solar fuel generation or for indoor electronics because it can give us a quite high open circuit voltage. And we designed the perovskite with 3 band gaps about 2 electron volt and 1.6 electron volt, and the typical nylon bandgap perovskite we use with a band gap of 1.2 electron volt. But when we when we wanted to make the triple junction solar cell, one of the challenges is the front cell, because we have to use a quite high ratio of bromine in this composition. So this film, the surface is quite rough. And when we want to spin coat a PTAA whole transport layer for the middle subcell, then it will give us a challenge because the VOC and also the fear factor is quite low. So later we find a strategy that maybe we can first spin coat a nickel oxide based nanocrystal to feel the values of this rough surface. Then maybe we will get a better film for the PTAA whole transport layer. And through these strategies, we can see here that we can get much higher open circuit voltage and also the fear factor values. And finally, so we can get a quite a reasonably good triple junction solar cells. So the efficiency is almost 20%. And the VOC value is quite high, so it can be above 80%. But from the EQE spectrum, we can see that for the 3 subcells, the current matching is not easy. So it is still quite a challenge to get a current matching condition. And also due to the introduction of several more charge transport layers, we can see that the optical losses is higher than the tandem devices. So here I just give a short summary about my talk today. So the first take-home message is that it is important to prevent the tin oxidation in the precursor solution. So what we can do is we can add some metallic tin powders in the solution. So in this way, we can achieve longer diffusion lengths and also higher efficiency in the perovskite solar cells. So we also develop a tunnel recombination junction that can enable us to get a high performance tandem devices without the use of the sputtered ITO layer in. And also we develop another strategies to improve the performance and the uniformity and also operating stabilities for larger area all-perovskite tandem devices by adding a surface anchoring sweeter ionic antioxidant additive in the precursor solution. And we also show that by using all inorganic charge transport layers and MA-free perovskite materials, we can get a quite thermally stable tandem devices. And we also demonstrated the solution processing of all perovskite triple junction solar cells, although the efficiency is not quite high currently. So finally, I have to thank all my collaborators who helped us a lot in the past few years to make great works and all my students in the group. And thank you for your attention. And I'm looking for the questions from all of you. Thank you.
Yes, thanks a lot. I'm giving a kind of applause here for everyone. Very, very impressive talk, especially the stability results, very nice. The procedure is now that I will have a look at my other window here to ask a few questions from the audience. I think we should take the time to take a few questions despite the slight delay that we have due to the technical issues. My apologies for that, by the way. So let's have a look. I think there were quite a few questions related to how you can make it happen that you deposit actually 2 perovskite cells on top of each other, solution-based. So there is one that says, does spin coating the water-based P.PSS damage the wide bandgap solar cell in any way? Or is protection by tin oxide and gold already enough? So
this is a very good question. That yes, I think the protection of the top cell is very important if you want to do the bottom subcell by solution processing. So typically we found that this atomically layer deposited tin oxide is very critical. So we have to find a good processing condition to make sure the layer is very conformal on the surface of the top cell, and also is very compact. And usually we, after making like a 20 nanometer of this tin oxide layer, typically we can meet those requirements, and we can do spin coating of the P dot without any problem. And of course, and also for the narrow bandgap perovskite. So I think if you find that after deposition or spin coating of the P dot layer, if the perovskite is not damaged, then you can easily just do the following layer of the narrow bandgap perovskite, I think. Yeah.
Okay, thanks. There's another question related to the tin oxide ALD process. So the question is, how can you actually realize this process on top of the tin lead perovskite by using a water-based process for the ALD? So since the tin lead perovskite should usually be quite sensitive to the water process, and the tin should be oxidized. So the question is basically, how can you realize this process here?
Yeah, it's also very good question. So in the beginning, we also thought that it would be impossible maybe to have this tin oxide layer on top of the mixed lead tin perovskite. But later we found that the processing temperature is very critical. So we can only do this processing like on top of the mixed lead tin perovskite below the temperature of 75 degree. And if we go above like 80 degree, and the performance of the solar cells will be very poor. I think at a low temperature, maybe the layer of the fluorine, the carbon 60, is quite a good like a protection, because the water injection of this process is quite a small amount of water injection. And I think, and it's also very critical to control the amount of water like you get inside the chamber. So this is also a very critical parameter when we do the processing. So usually if we make the tin oxide layer on top of the lead based perovskite, so this parameter is not so critical.
Yeah. I think there's a related question here actually. So how reproducible is this tin oxide layer? So is it actually a layer, or rather some surface chemistry taking place there, considering also the thickness and, as you mentioned, then the low process temperatures? So are you confident that this is really a tin oxide layer, or could this be chemically a little bit different from the usual high temperature tin oxide?
We haven't studied like the composition or properties of this layer in a very deep detail, but we usually found that this layer, the processing by atomic layer deposition, is quite reproducible, especially on top of the lead-based perovskite. But and usually like the reproducibility is not a problem, at least in our lab. So almost all the lab members can make a good layers on top of the lead-based perovskite films. But we do find that it's quite tricky and interesting that to deposit this layer on top of the lead tin perovskite layers. It seems that it's quite sensitive to the processing parameters. Even in my lab, not everyone that can make a very good performing devices like on top of the mixed lead tin perovskite. So I think maybe like the control of the water injection, and also the temperature, and also the purge time could be quite critical, could be, yeah. But we haven't even studied this in a very detailed. So.
That sounds like an interesting topic. As a photo with photoelectron spectroscopy, I think it might be interesting to look at these layers and check if they are really yeah, proper tin oxide. Anyway, I think we have to stop here, although there are still quite a few questions in the chat. Maybe you can take your time to answer a few just in the chat. I think we need to move on to the next speaker.
Thank you.
Before that, thanks again, Hairen, and I would invite Steve to the stage, the virtual stage.
Hi, Lars. Hi, everybody.
Okay, so it's my pleasure